Representations of functions. There are four possible ways to represent a function. Verbally, by a description in words; numerically, by a table of values; visually, by a graph; algebraically, by an explicit formula. Now, if a single function can be represented in all four ways, it's often useful to go from one representation to another to gain additional insight into the function. In example 2, we started with an algebraic formula and then we obtained the graphs. Now, but certain functions are described more naturally by one method than by another. With this in mind, let's re-examine the four situations that we considered at the beginning of this section. In Part A, the most useful representation of the area of a circle as a function of its radius is probably the algebraic formula, a of r, which is equal to pi r squared. Though it is possible to compile a table of values or to sketch a graph, half a parabola, because a circle has to have a positive radius, the domain is all the r's such that r is greater than 0, which would equal 0 to infinity, and the range is also 0 to infinity. B. We are given a description of the function in words. P of t is the human population of the world at time t. The table of values of world population provides a convenient representation of this function. If we plot these values, we get the graph called a scatter plot, and you'll see it below in figure 9. It too is a useful representation. The graph allows us to absorb all the data at once. What about a formula? Well, of course, it's impossible to devise an explicit formula that gives the exact human population, P of t, at any time t, but it is possible to find an expression for a function that approximates P of t. In fact, using methods explained in section 1.5, we obtain the approximation P of t, which is approximately f of t, which is equal to the following number, times this number raised to the power of t. And we can see that figure 10 shows that it is a reasonably good fit. The function f is called a mathematical model for population growth. So in other words, it is a function with an explicit formula that approximates the behavior of our given function. We will see, however, that the ideas of calculus can be applied to a table of values. An explicit formula is not necessary. So here we can see that this is the scatter plot in figure 9 of our data in that table. And so some of the ideas you'll see in section 5, we can come up with a formula to approximate this particular scatter plot. So when we graph that function, we can see that it's approximating what we plotted in the scatter plot. Now, the function p is typical of the functions that arise whenever we attempt to apply calculus to the real world. We start with a verbal description of a function, then we may be able to construct a table of values of the function, perhaps from instrument readings in a scientific experiment. Even though we don't have complete knowledge of the values of the function, we will see throughout the book that it is possible to perform the operations of calculus on such a function. In C, again, the function is described in words. The cost C of weight W is the cost of mailing a large envelope with weight W. The rule that the U.S. Postal Service used as of 2008 is as follows. The cost is 83 cents for up to 1 ounce plus 17 cents for additional ounce or less up to 13 ounces. The table of values shown in the margin is the most convenient representation for this function, though it is possible to sketch a graph of this as well. Now this means that between 0 and 1, if our ounces are in between 0 and 1, and you can include 1, it's going to be 83 cents. If it's between 1 and 2, including 2, then it's going to be $1, and so on. Now when we graph this, it's going to be a certain graph that we will see in example 10. In part D, the graph shown in figure 1 is the most natural representation of the vertical acceleration function a of t. It's true that a table of values could be compiled, and it is even possible to devise an approximate formula. But everything a geologist needs to know, amplitudes and patterns, can be seen easily from the graph. The same is true for the patterns seen in electrocardiograms of heart patients and polygraphs for lie detection.